So we move on to Jorge, who will give us overview of the low latitude valley region and some possibilities to work together with ground-based data.
Okay, Claudia, thank you. Thank you. Thanks for the organizers. I hope the sound is good.
Sound is good.
Okay. Well, thank you, Claudia and the organizers. It is my pleasure to be in this workshop of this exciting Daedalus mission. As you can see from the title, the low-latitude ionospheric valley region is highly relevant for Daedalus and Daedalus for us. The mission, the observations, and the science that we are doing. I would like to acknowledge my co-author, Dave Heisel, who has contributed with a lot of the material related to the nighttime echoes, and a special acknowledgement to the members of an EASY team that I'm leading, that, as you can see from the title, is highly relevant for Daedalus. I have organized the talk into a couple of the region. We have heard a lot about the valley region in general, all the lower thermosphere, ionosphere, or as is mentioned in Daedalus, is where the atmosphere meets the space. So I will introduce some important and relevant characteristics of the low latitude region, and then I will go to the echoes, and to the echoes like this example here, and a spread graph map from Jicamarca, and the normal valley region will be below 200 kilometers. And as you can see from the intensity, the 200 kilometers and below is not empty of echoes or observations from radar. And finally, I will try to do a connection to Daedalus plans. So from Daedalus mission design, if you see 150 kilometers is there, and from what the science and topics that I'm going to mention, 150 kilometer is the last name, is the definition of our studies in the last 20, 30 years. So in situ measurements, like plasma density, temperature, ion drift, and neutral density, and winds, and ion neutral composition, and electric fields, as Daedalus is planning to do, are very welcome, and I think we'll have a complementary use of our expertise and Daedalus contribution. So the low latitude valley region, in the first one of the first talks, we learned about how complicated is this region, but what more focus on the high latitudes. And here I want to focus on the low latitudes. At the low latitudes, and some of these concepts are general, but as you see, the geometry will make us a little bit unique. So the transition is the transition region between the moleculars and the ions and the atomic components. Collisions starts to be less. Is the area where the photoelectron production rate is the maximum. Is the area, according to Arecibo observations, where intermediate layers exist, metallic ions. The TE, the electron temperature to ion temperature, the ratio is one of the largest during the day. And something that is not notorious in the high latitude, but at least in low latitude, is that the electron density, at least below 160, 170 kilometers, the gradient is almost absent. It's almost a flat gradient there. It's about 160, 170 that the gradient is steeper, but between 110, 120 and to 160 or so, the gradient is not much. And at night, the electron density content is almost nothing, or is very, very small. On top of that, that is common to most of the valley region, is that the geometry, and here is a sketch from Dave Anderson, the geometry is different than at high latitudes. Here, the magnetic field is almost parallel to the magnetic equator. So, for example, when we discuss parallel currents, we are not discussing currents coming vertically, but now we are discussing currents that are mainly, or field aligned currents, mainly that go horizontal. And in our case, we'll go from E region in the south to E region in the north, and covering the 150 kilometer region. So as this is something that we use in the past in one of my AGU talks, this region is where terrestrial weather meets space weather. So to understand the ionospheric dynamo, and that is another important aspect of the low latitudes, here, at least during the day, the E region dominates the electrodynamics of the equatorial low latitudes due to the high conductivity of the E region. And in a way, the low latitude is a sensitive region to lower atmospheric forcing, given that the E region is where the tides and gravity waves are strong and conductivity is high during the day. Any effects happening in the E region are propagated through magnetic field lines to the F region. So in the high latitudes, the effects from the magnetosphere of the sun will be more pronounced in the valley region. At low latitudes are the lower atmospheric forcing waves, planetary waves, gravity waves, tides will be, I would say, would be more pronounced. So both ends of both latitudes will be important for that Daedalus. Going to the nighttime echoes. Here is again the picture of Jicamarca spread F echoes between 100 and 1,000 kilometers. And below 200, during this night in October 1993, you see that the E region and F region are connected through what we call, or Woodman in 1976 called the valley region echoes. And if you make a zoom of those echoes and assume that the ions on the plasma is drifting across the radar, then we are talking about scales, undulations in the irregularities that are tens to hundreds of kilometers, tens of kilometers in this particular case. So it's already an indirect indication of the type of waves that can be acting in this region. More recently, over Jicamarca, we conducted, well, that's 10 years ago, 15 years ago, we conducted an experiment where we again observed these irregularities, in this case between 120 and 150 kilometers at night. This is local time after sunset. And from the RTI, we see that it's highly structured in time and space. But this experiment was accompanied by imaging, synthetic aperture imaging within the beam. So instead of looking at how the echoes are drifting or assuming that they are drifting, now what we are able to do is get the image of them. And when we do the imaging, what we see, if I don't tell you that these are plasma, and I told you that these are clouds, what we are seeing are clouds, well, in this case, clouds of plasma irregularities, going across Jicamarca with wavelengths and structures on the tens of kilometers and lower. At the time, we didn't know what type of instability or why the echoes were there. So Heisel et al. A couple of years ago put together gravity waves and a packet of gravity waves and a tidal field. And these wind fields of gravity waves and tides were fed to a 3D electrodynamical model that connects the E and F region and takes into account conductivity and the geometry. And after combining that, they were able to see the response of that model in the electrodynamics, that indeed the valley region is modified by the gravity waves in a way that creates not only the undulations that we see, but also creates the necessary conditions to have irregularities so the radar can diagnose this region. So this is the response in the electron density, these small oscillations these small undulations induce the gravity waves induce field-aligned currents that at the end produce these nighttime or twilight echoes as we claim. As I said, 15 years from the observations, recent modeling, we are now able to understand why are there. If we understand, now we can do connection to gravity waves, like in this particular example. Another source of information in the low latitude region from ground-based radar is the so-called 150-kilometer echoes. And these echoes, although studied since 1960 until recently, until just a few months ago, we were not able to understand why they were there, what are the gaps between the layers, why they stop at the lower boundary of, let's say, 135 kilometers, and what are the pairs, what are the oscillations in time and altitude of these echoes. However, even though we didn't understand them, they have been the source of electric fields in the equatorial region in the last 20 years. We don't understand the echoes, but the echoes follow the plasma, the Doppler shift of these echoes follow the E cross B drift of the plasma in this region, and people and numerical empirical models have been developed on these electric fields, and as far as I know, is one of the major source of electric fields at low latitudes and 450 kilometers. So that's one of the reasons we put together this EC team to get the echoes and to understand the dynamics on the region. So as you can see, the variability is high in terms of gaps and structure in the echoes, but not much in the electric fields shown below. In addition, if you zoom in these echoes, and now we are showing, instead of 8 hours, we are showing almost an hour, we see a strong modulation in time in the echo structure, with modulation of few minutes, 5 to 10 minutes. And also we see a clear gap between layers. And I'll show you later that this gap and these modulations, we have now a much better understanding of what is going on, and we could use them for connecting to understand the undergoing processes behind the instabilities. And in addition, in 2013, with Erhan Kudeki, we wrote a paper and we did an experiment where we find that most of these echoes, the echoes are a combination of enhanced incoherent scatter echoes and field-aligned irregularities. For many years, they were attributed to field-aligned irregularities, so we were looking for a source of energy or for a source of instability that were field-aligned. And this discovery of that they were natural enhancing coherent scattering has helped us to, as you see in a couple of slides, to determine what is the source of energy for the presence of echoes. Related to previous talks in terms of planetary waves, tides, and gravity waves and the interactions of them, these echoes are in a way painting these dynamics that we are discussing, that we are elusive in our current observations. These are 9 consecutive days of 150-kilometer echoes in the same scales of altitude and time. And as you can see, from day to day, there is a huge variability. And variability that we claim and we believe is due to atmospheric variability, neutral variability. No, the interactions of gravity waves, tides, and planetary waves when we look at the larger scales. So recent results, and most of them related to the EC team that we put together, is that by combining the observations with Wacom X, now we are able to get a good connection between the morphology of the echoes and the electron density profile. Here to the left is a typical example of Hikamarka And to the bottom part is electron density contours from Wacom X with specified dynamics. In this particular example, what Gerald Lemacher et al. are showing is that the gaps in the 150 kilometer echoes and the shape are associated to the electron densities. Moreover, these electron densities, they postulated and they hypothesized that could be a link to an upper hybrid resonance condition that could be the source of energy for the echoes. On another recent work by Pedatella et al., during a 150 kilometer experiment where there is a strong solar flare in 2000, in this, I believe was 2006, this solar flare, here is the GOES X-ray flux. When the solar flare comes, the 150 kilometer region came down and the echoes, also the 150 kilometer echoes came down. Using Wacom and feeding these solar flare-like conditions, we are able to reproduce almost one-to-one the increasing of electron density and the decrease of the contours of electron density that accompany these 150 kilometers. The two are connected. These are normal conditions. These are solar conditions.
Okay, there are 2 minutes.
Oh, okay. And 150, and then more recent. Thank you, Claudia. And more in other observations from high-resolution Viper, we see that gravity waves are observed in electron density, and these gravity waves are precisely measured also by 150 kilometer gaps. So I'm showing waves and gravity waves effect on these 150 kilometer echoes in all. And let me finish, well, close to finish, that the most recent work by Longley puts solves, I would say, 70 to 80% of the questions that we have had for more than 30 years. So I won't go into the details, but by combining upper hybrid instability, that has been postulated for other phenomena, but not applied for 150, and solving the equations, combining with thermal Landau damping and collisional damping rate, we are able now to understand why the echoes of enhancing coherent scatter are there, why the gaps are due to thermal Landau damping, and they are multiple, they occur on frequencies that are multiple of the gyro frequency, and the lower limit altitude is dominated by collisional damping. So for people that have been listening to this type of research, this is a huge improvement. I will share the presentation so you can see that some of the questions that we have in our group are related and could be related to be investigated with Daedalus. It would have been nice to have Daedalus in our group. So maybe in 10 years or a few years from now, we can build a group again and combine satellite and Daedalus and ground base in Air Force. So to finish, these are here to the right, the Daedalus objective. And I think this is how we can contribute to Daedalus. Of course, one way is CalVal. We do have electron densities, electric fields, temperatures. Combining the two, we can go after a smaller scale plasma waves and the instabilities behind. For that, one of the questions will be, could Daedalus measure field-aligned currents, small field-aligned currents in the low latitude that can help us, and electric fields that can help us attack these smaller scale plasma waves? The mesoscale plasma neutral interaction. Here, now that we have a good theory of the echoes, we could use them not only for electric field measurements, but also for gravity wave modulation of in the electron densities by looking at the gaps. And of course, by looking at the gravity waves and electric fields and the day-to-day variability, we can be looking at coupling effects like it has been shown in sudden stratospheric warming events in the past. Thank you very much.
Thanks a lot, Koki, for, again, a very nice presentation. Are there questions or comments by the audience? I would have one question concerning the field align currents you mentioned, which are almost horizontal, of course, in the low latitudes. Has there been already 1 or 2 measurements of those, for example, by rockets or something, or are these field align currents, you say, are derived from theory and models only?
The field align currents, there are no observations. As you know, this region has been measured only with a handful of rockets. So there is no field align measurements of electric fields, as far as I know, or currents. There are a couple of indications that they exist. We don't have an idea of the magnitude, but given that they exist due to a connection to the E region, we expect them to be small but important.
Okay.
One of them is that when we look at the spectrum gets asymmetric. The ion line gets asymmetric from left to right in a fraction of a minute or so, with a decrease of 70–80% from one part to the other. And the other is by the high oscillations that Pablo Reyes and Erhan Kudeki have observed in the echoes, pointing to alphenic waves. But a number per se, we don't have.
Mm-hmm. Okay, thanks a lot. Very interesting. There's one question by Jonathan Kral, asking, since these 150-kilometer echoes are always present, do they always show gaps that remember gravity waves?
Yes. Yes. The answer is yes.
Yes. And there's another comment from somebody in the chat, MLE, pointing out the connection of ground-based observations. But if you can answer that in the chat, Kogi, that would be great.
I'll do that. Thank you.
Thank you. So thanks a lot. And